Okay, let's get started. So tonight I want to keep working on the activation virtual machine. So yeah, it's yellow because I just rebased it. So what is it about? So I'm working on a neural network inference engine called Tract, and in an engine like this, there is a mix of, in any neural network, there is a mix of affine operation, which are essentially matrix multiplication, which are already optimized a lot in Tract, and they alternate with activation function, which are violently nonlinear. That's the ReLU, sigmoid, hyperbolic tangent. And these usually are computed on an element-wise basis, so they tend to be easier to compute than the matrix multiplication. And what I'm trying to do is I'm trying to get this computation vectorized. So the geometry doesn't matter. Tensor can be seen as just a big slice of number, and I need to do the same operation on each element. The only trick is I want to do it as quickly as possible, or as practical at least. So we have a couple of functions that are commonly used in neural networks. So some are very simple. It can go from ReLU, which is max with 0, so it's flat in the negative value, flat on 0, and then it X identity on the positive values. But it can be a bit more complicated, like this one or that one. This one is actually super interesting because it solves some. It's interesting from perspective of machine learning, and it's also not too complicated to compute because it just has two multiplication and then simple arithmetic stuff. There are a couple other which are interesting, like hyperbolic tangent and sigmoid. They're interesting, but they are already very optimized in Tract. So I don't know what I want to do if the new implementation is comparable in terms of performance. I may switch to it because it will be easier to maintain and to extend, but I don't know. These are more complicated to compute because the right way to compute this is not to go through the exponentiation function, but to use a rational approximation. So it's the quotient of two polynomials on X. And this is what is implemented and already vectorized by hand. So now what I want to do is, what I started to do over the past few sessions is we define a virtual machine. We define a little virtual machine which is which has about dozens of instructions. Ops. That's the list of instruction. And with this instruction, we managed to compute a relatively important subset of the activation function that we need to implement standard neural networks. So for instance, we encode our activation functions. So these are the reference implementations. And did I forget to add one file to the... no, it's definitions. Okay. And so this is a ReLU function, so max with 0. So there is one single instruction which does a max with a constant 0. But we can have more complicated stuff like soft sign, copy. So the data received in the A register. So we make a copy in B, we take the absolute value, we add 1 to the absolute, we put it in the below fractional tray, as the denominator of a function, and we multiply by B always multiply by b, which is x because we moved x to b. So it computes x over 1 plus absolute value of x, and so on and so on. This one is the sigmoid function. I didn't do the hyperbolic tangent because it's more or less the same. And so for the sigmoid, we need some instruction which are fuse, multiply, and add. They are not exactly the one that we will have on the processors, so we'll have to do a bit of register swapping around. And one thing to say here is I choose to put the constant in a separate table, and I'm not 100% sure it's the right call. So 0 and 1 are always the constant 0 and the constant 1 because basically we use them all the time. And then the table start by 2, 3, so 2 is minus 18.6, 3 is 18.6, etc., etc. So this does max with constant 2, which is these values. So that's just for clipping the very negative value and the very positive values with this one. Okay, what we did last week is we did a couple of benches of these, and it was looking okay because, for instance, let's try hard swish. Basically, what we realized, and it was not a big surprise, it was just as expected. The reference implementation is better than our VM when we compute a very small number of values. But as soon as we get running over slices, then the VM cost is amortized, and so at some point around 256 values usually our implementation, I mean the VM implementation, gets better than the reference implementation, and this is with just Rust code. We didn't do any assembly yet. We just trying to get the data, get the computation in as clean a way as possible so that the optimizer can do whatever it wants. So for instance, here with one single value, the reference implementation compute 121 millions of elements per second, while the VM is 10 times slower. And if we use the vectorized implementation, it's even worse. So yes, we have three implementations. We have the reference implementation, we have the VM basis implementation, which takes one element at a time, and then we have the VM vec implementation that operates on the entire chunk of data. And here you can see that the reference was at, let's look at the 1000 case. The reference implementation is 800 millions of elements per second. The naive implementation of the VM is very bad, but the vectorized implementation actually outperforms the Rust reference implementation. So we kind of have already win, but I want to go further and see what we can do with assembly. And before we start doing assembly, there are several questions. First, I wonder at what time I will want to move the current new code inside Tract properly, because Tract offers, I mean, there are some utilities in Tract to work with assembly files that I don't want to basically reinvent. And there is also the question of the architecture. I not a big fan of Intel, so I think I'm gonna move away from this, from Tsar, the machine on which I'm logged on right now, because this is an Intel machine. Or else I could use emulation. I'm just wondering how to work, because I have a laptop which runs, which is an Apple M1, so it's actually an ARM system, which is what I would like to work with. The problem with this is it's also the machine that handles all the streaming and video and stuff, and I'm a bit worried. We'll try. And I get I get conflicting information on the CPU load. Okay, what we can do is we can try with trying to make it work with QEMU in assembly, and then we can just run the bench on the M1. Okay, that's the plan. So what we're going to do is first we need to move the code away from. I mean, there is something else that we could try before going there. It's portable SIMD, but this is really portable SIMD is a feature in LLVM which has some binding in Rust. But it's so fragile, and so, I mean, every time I tried it, I was disappointed. So I don't want to do. No, I don't. We're not going there. Okay. So I'm decided. It's going to be ARM 8. I'm going to start writing it on Intel, doing all the refacto and everything. And even the test on Intel, and then run some bench on an Apple M1 system. Let's try this. Okay, so what I have in tract, I have several crates, but the one that we are interested in, oops, that's too big, is linalg. It stands for linear algebra. It contains much more than linear stuff, but the name is, well, that's the name. And so we have several things here. We have frame, which contains generic Rust code that works for all the architectures, and which is called for all the architectures. We have generic, which usually contains Rust implementation of the lower lower level routines. So for instance, when you run tract on a new architecture, let's say RISC-V architecture, for which we do not have handmade optimized kernels, linalg will combine code from frame to deal with the upper layer part of the computation with code from generic, which contain the lower level part written in Rust or portable. When you move to Intel or to ARM, then it will be, well, obviously different, because we will still be using frame, but instead of using the generic kernels, we will use the architecture dependent kernels. And if we look at one of these files, let's look, for instance, at that guy. So that's ARM 8, more or less standard. We just have a declaration for kernels, and this big macro, M stands for matrix multiplication. This big macro will look at, I mean, it will define the kernel. It will it will define it as a Rust object. It will set up tests for the kernel, and it will also well, that's about it. It will define the kernel and it will run the test on it. And the idea, this is a function that is an extern C somewhere, and the actual code of the function, the assembly code, can be found in 64 simd in one of these files. So I don't remember which one we were looking at. I guess it was that guy. So that's the assembly itself. And still there are some. I'm using a web template engine to write assembly because it was more fun like that, I guess. And also because it allows me to have specific parts which are depending on the actual system. So for instance, this file will be generated for 3 cores. It will be generated for a generic core, a Cortex A53 core, and a Cortex A55 core, because these are of specific interest for my employer, and because they really need a specific implementation, while most of the other ARM8 systems that we have looked at can work fine with a generic implementation. So that's the basic of it, and so now I think what I want to do is I want to reproduce this system for the activation function. So we'll start easy with the Rust implementation, and so basically we will move code around from the linalg activation, prototyping, through SRC. So we have the definition is in lib, reference is a reference implementation that we will be using for tests, for integration tests, and definitions is the actual functions programs. Could call them microcode, I guess, or macro code. I'm not too sure at which level we should put ourselves. So let's have a look at this. So on top of this, in linalg, we have this mechanism that will try to choose. So we have this list of ops, which are basically the optimized routines that we support in linalg. And by default, we use these generic operations, which are frame plus generic Rust code, so they work everywhere. But then we have this function that has some architecture-dependent plugs. And for each architecture, it will replace these guys are functions. So it will replace these functions, these function pointers, by more optimized function pointers for the architecture. For instance, if I look at ARM64 simd, so that's the file we were looking before, homegrown, SRC, it should be there, yes. So here we have a bit of CPU detection. So these are the main CPU that we are distinguishing. It doesn't mean that we do not support all ARM8, because all can work with a generic kernel, but these are the ones for which we have specific stuff done. And then, yeah, so basically this is a plug function that will put the right callbacks in the default structure that we were looking before. And it's done just once at the startup of tract, and then from there, each of these functions will in turn pick the right implementation for an operation. So what we are actually discussing is we are going to add a function here, which I think will be activation F32, and this function will take I mean, I'm not going to do it right away because there are a lot of things that will be lacking, but it will be a pointer on a function that will, because for these guys, so that's the big one. That's the matrix multiplication in single precision. So for these guys, once you have picked one system, one architecture implementation, you still have several implementation of the kernel that depend on the geometry of the problem. But I think that for the activation function, we will be on the same kind of idea than with this one, and so which are activation function, and so we will have S is for single precision, so that's F32. Activation. And will it be element wise? Can I reuse this thing? So let's have a look at this SRC frame element wise. So how does it work? So there are a lot of macros in this code. Bit complicated to visualize, I guess, but yes, there is a trait element-wise here that takes a function run, which in turn takes a slice and change the slice. Okay, so that's it. Looks like something we could reuse. The only difference is that we have a second argument, which is the actual function we want to compute, so the program. So if we go this way, it's not exactly the same thing, because we need to pass the program somehow. No, that will not work. I mean, it would work if we were doing something like that. Obviously, which is because it's really the same as this. But what we are going to do, we will need something a bit different. We will need a function that will take a program let's call it microcode. And that will build a runner, I guess, something. Let's try to see if we manage with that. So to do this, I will need to add some code to frame. And it will look a bit like this one, but not exactly the same. We have a temp buffer here, which is a thread local. Yes, that's a buffer that we can use. I mean, this is to manage alignment issues. If the buffer that we are given, that we want to compute, is not properly aligned, then this temp buffer will allow us to, I guess, manage the beginning and the end of the slice, and then we can deal with the middle in an aligned way. Okay, let's split this code because it feels like it's not dependent on, it's not something that we need, something specific that we need for the element wise, frame.rs will have a module called temp buffer. Okay, and we need some includes, so layout come from alloc. We need to make this guy public if you want, I guess. Okay, and here I will have to fix this guy, I guess. Temp buffer, I can import it. Use create frame temp buffer. I will re-export it at the frame level because the idea is we want to be able to reuse it if we need it. So I will make it pub self use temp buffer. Okay, so this should be fine, and this should compile too. Okay, temp buffer must be public, obviously. And I can make this public too. So why is it useful? So this will define, so it looks like, so there is a lot to unpack here because I'm using the macro past, which is a proc macro to generate module name with a function. So the function is the extern C function. SRC frame, if I'm looking at an actual implementation like ARM64 slash, so we have Tanch and sigmoid implementation, which I guess will be defined, I hope, but nope, they're not defined here, they're somewhere else. So if I look at frame sigmoid, yes. So sigmoid implementation, it will use EW implementation, which is defined here, which does, so extend kernel is another macro that actually define the extend C function, and one of the interesting thing with this macro is it suffixes the function name with an ID, which comes from the build system, the build.rs system, and so we can have several versions of tract in the same space. Because also the that's one more reason to use the web template engine, because I'm suffixing the function in the assembly too, so that if two versions of tract are linked in the same executable, there is no issue with difference of expectation between the assembly and the C code. Yep, it's a bit complicated. Anyway, so the EW implementation, it defines, so TI is the operating type of the operation. So it can be, most of the time it will be F32, but sometimes it's F16, like for these two functions, actually. And NR is the number of, it's a number of elements that the function will process per iteration. Because there are two levels of loops. So So this is the number of elements that the inner loop, the one which is written in assembly, will operate on. I think it is expected that the slice is aligned on alignment bytes, the slice that we are going to process, and also that the len, the number of elements, is a multiple of nr. I think that was a contract, which is probably the same one. I mean, the one that we want to apply to the activation functions. So if we look at the main function, so we are pulling the temp buffer that we created as a thread local, so there is no conflict between threads if two threads are running tract. And we are making sure that the temp buffer is at least nr times the size of the operating element, and also aligned to whatever we want it to be aligned. So we have a function that will compute via the temp buffer, and we are looking at the prefix. So the prefix will be align offset vec as ptr.align offset. I'm not sure what that does, but the point of this is clearly to compute the elements that are not aligned at the beginning of the slice. So if we need an alignment on 4 elements and the slice starts on, let's say, an offset which is not multiple of 4, then let's say 1, then we have 3 elements to process, and so that's the job of this to first copy them to the temp buffer, which is aligned, and compute them here, and finally put them back in the slice unaligned where they were expected to land. Then we process the mid part of the slice, which is aligned by just calling the kernel function, and finally we call again the kernel function for the unaligned bits at the end. So that's exactly what we want for this is exactly what we want to do for the activation function. We have the same problem exactly. So we could make this, I mean, here we are on element-wise struct, and we are implementing the element-wise trait. So what we could do is define another element-wise struct that will be the activation ampl, and it will implement the element-wise trait, and the element-wise trait is here, and actually I could maybe trying to think if I can move most of this code up there in the trait implementation, but no, because here we have we have these constants which are really dependent on the struct itself, so we don't want okay, no, it won't work, but that's fine. We can still do interesting stuff. I guess we can still try to isolate this bit of code. And just pass it the k.run function. That could work. Let's give it a try. So this function will have the same kind of type dependency at that one. I'm making it pub because I will want to use it for the activation stuff. Run element-wise aligned, and it will take the slice, which I called vec, which is not a great name, but that's fine, plus it will take a function something that yeah, a function of yep, and that does nothing. I mean that doesn't return anything. Okay, that should work. So now if I put this, all this code, I will also take the time buffer. And maybe I can even take this actually. Put it there. What is this? So this is not depending on k explicitly, it's depending on t. And so the function return a tract result. So t is highlighted when it's defined there, that's fine. And I also need, so t data time size of this will be fine, but I also need the nr and alignment bytes. So let's add them here. Usize, align, usize, alignment bytes. So and so that's nr. Okay. And again, oops. So this is the function f of tmp. This is alignment bytes. What's wrong? No, this is not good. It had to be this. Align offset, alignment bytes, parents, then min. Yeah, okay, that's good. nr. Calling f of these. Okay. And now the logic say that this should be just run element-wise aligned vector. So f will be k run, nr will be k nr, and alignment bytes will be this, and I can discard all that. What? Yeah. Okay, so now we have this function that we will be able to call also on the activation trait. So let's try to define the activation trait now. So the temp buffer, I'm tempted to move it to, yeah, I'm moving it to the temp buffer space. And actually I will call this run over slice with alignment. And I will move it to temp buffer. And temp buffer will be renamed align slice, guess. And so, yes, it's okay. LA datum is just super type for F16, F32. Anyhow, okay. Okay, let's make this compile before we move on. I'm gonna use tract result here. No reason not to. This was a legacy stuff. Run over slice with alignment. So I need this function. It's public. I will make it public, but only in the crate. Okay. 68. So I need to access this guy. Oops. Okay, we're compiling. And I no longer need to make temp buffer public, which was expected. Okay, let's do a pass of test. Okay, nothing seems to be broken. I'm adding this guy. Yeah, I wanted to rename it. So temp buffer. How did I call the function already? src frame temp buffer. The function is run over slice with alignment. Slice runner. Slice element wise. Helper. Element wise helper. Yeah. Okay. And then I need to rename the other guy. Okay. It's not on the Git yet, so it's just straight MV. src frame element wise helper.rs with an underscore, which I don't think. Yeah, okay. Okay. Yes. Okay, let's commit this. Helper.rs git commit split. Okay, next. So now we can go back to element-wise, and we have this function, this trait, and we are going to mimic it or copy it, and the only difference is in the run function here. Well, we will add the program. Okay. So first the trait. So this is a trait that is exported to this is a trait that is exported to outside of the crate. So it will have program, which we need to define yet. Program. I'm gonna just put a placeholder for now. Okay. So we have this engine that can compute activations, and so this is what is exported. I mean, this is what is shown outside of the crate. So the other crate will have to build the program, and then, I mean, it's already have mosquitoes. And then once the program is defined, we can call this function run on an arbitrary vector to get the results, and the result will be put in place in the slice. Okay, then we have our abstraction layer for implementations. So frame.rs has a new module called activation. So hopefully it will compile. Yes. Okay. Let's start with the include. Here we go. Okay, then so that's the trait. Then we have at the lower level we have this kernel trait, and the kernel trait will represent a physical implementation, so a Rust or assembly for our function, or for the engine more than the function, because so it will be an activation kernel, and so this will call activation. I'm trying to keep these names short because if they're too long, I mean, then it has, I mean, it's just for code formatting. We have this long list of implementation in many places. So the name, it's better if the name are tiny. I mean, it's not super critical, but okay. And so we need an intermediate struct that will actually do the work of while running the function that we just isolate from element-wise. So it will be called, so it will be this guy. And it will be called activation implementation. So this one is not exposed, but it's implementation of these in a box activation, which will be returned to the above layers ampl. So it's not element-wise, it's activation kernel. And we implement the trait activation for element-wise for activation implementation, which is our struct. It will be dependent on an activation kernel. And so it will also receive the program. And so this function will be different because, I mean, we did it already. Did we? No, we did not. So here we also need the program. And so the function here will be, it will receive a slice and it will run. Okay, run with program and slice. Nope. Yes, just need to import it. Okay, so we have the basic structure that will allow us to write kernels in whatever way we want, either in Rust or in assembly or in C or whatever, and wrap them into this activation amp structure to present this to the higher layer code, to the code in tract core, for instance. So one other feature of this, I mean, one of the characteristics of this part of Tract is it's heavily tested, and I don't want to write the test for every kernel, so I use macros again to generate the wrapper, so the wrapper instance of this structure, to define these. Yeah, so I still need implementation of kernels so element-wise. So we have element-wise char, and we should have a macro. Yep, that's the macro that we need to steal. And this macro will create the kernel. So the kernel is just it's a struct which is here, which takes the name of the kernel. So the kernel is a function in assembly or in C. So it has a name which is in snake case usually. So we need this. I need to use this to prevent a warning, and I will have an activation char for function. So that's fine. This is fine. This is fine. This is okay. And here I have the program. And so the assumption is we have some kind of So in the element-wise case, at this point we are in FFI. We are writing. I mean, we are calling C functions. So we cannot use slice anymore. So we split the buffer in a pointer and its len, and the program we will see what we need to do with it. For now, this is just this is essentially a placeholder, and this will be act implementation. So I'm using EW for element-wise and act for activation. Okay, why is a warning? Because it's never used, I guess. Yes. Okay, and what else do we have in element-wise? We have the macro, we have the top-level trait, we have the struct, we have the kernel, and we have some tests. And what do they do? What do they do? Test element-wise. So they expect a kernel. I guess they're used. Yeah, and this. Okay, so they expect a kernel and a reference implementation. So we will have later on. We will have to do something about that too, something similar to have. To port our tests. So we need the reference implementation, the values to test, and the program that we must apply, and a function similar to this one to ultimately call close enough. But this is basically just moving around some code that we already have in the other files that we did a couple of last week and the week before. Okay, so before moving on, before going on with the test, we will try to let's try to define program or see what we can use. Because what would be nice would be if we can make this so that this means that Rust will not try to reorder the fields in the structure, and as a consequence it will be a structure suitable for being passed to a C function or an assembly function that does whatever we want it to do. And if we look at what we designed the other day, so we have here. So we have register IDs. So these are easy to make because program is here. So it has a vector of op. So vector is, I don't think it's repr C, but we can easily replace it by a box of ops. So let's just try to do it like this. Okay, yes, no problem. So it's happy with, to my surprise, it's happy with the vector. Which probably means that there's something I don't know. Rust vector repr C. sure it doesn't mention vector. Maybe here. So vector has a pointer, capacity, and a len. The question is it repr C? Okay. Anyway, really, can I do this? Because there are two source of surprise here. First one is I didn't expect. What happens if I do this? Okay, so I suspect that it doesn't assume that the underlying I mean, it's not it's not transitive. Yeah. So program can be rep C even if it contains stuff which is not a rep C, I guess. Let's try this. Okay, so it's not transitive. So it's up to me to make sure that it does work. So I think I will keep that definition. I had another idea while we are doing this. So I want this to be rep C, which will be interesting. So I need register. Okay, let's pick these two. Because that guy cannot be. This one cannot be. I mean, if it is rep C, then I'm not sure what the representation is. So we will need to check the documentation. Because this stuff will not work out of the box. I mean, actually it will. No, it will. And I think I'm already using stuff like that. So the idea is size is fine, register ID, rep C. There is a case where I already have something like that actually. It's called fuse. Okay. And I have a fuse care spec, that's the one, which is rep C. So U size states what is the size of the discriminant. So for instance, this move will be stored as a U size of value 0 plus register ID and register ID, and register ID is defined as It's not defined. What if I make this guy U16? Oh, I cannot have both. Okay. Conflicting representation ints. So what if I ask U size? No. It's funny because that's what it accepts here, but I guess that's maybe because this one, nope. Huh. So this is working. So is it because we don't have any subparameter? Yes, okay. All right. Okay, so I'm going to stick to this. And I'm going to do that, I guess, which is a bit different from what I did. I mean, I didn't specify yet any U32 is better. My logic is on a 64-bit architecture. What would be a nice layout in memory for this to be read in assembly? And there are two questions in this. I don't want to spend too much time. I don't want to make it too complicated. And I mean, I don't want to make it too complicated for me to write, and I don't want to make it too complicated for the CPU to process. So obviously, all of these will, as it's an enum, all of these will take the same room in memory. And we could try to make it super small, like saying that the discriminant is U8 on 1 byte, that the register ID is also on 1 byte, because it's only 1, 2, or 3, so 2 bits would be enough actually. And then we have the constant ID, and we never have more than a few dozens of them, so all of this could be made U8. But if I'm doing that, then I'm gonna have to write quite a bit of code in assembly to split. On the other one, it's more compact, and it's 3 U8. Okay, U8. Yes and no. So I'm going to do this because that way the op will be 32-bit. And I think it's going to be easier to manage like that. I want to make sure of this because the assembly will depend on that. So I'm going to do a test. And I'm going to assert that std mem size of op has to be 4 because size of is in bytes. Yes, okay. Just to make sure. Okay. So, we have our memory layout for the program, I mean for at least the op. And now what I'm going to do is I don't want to mess with this. I don't want to have to deal with this stuff. So with the vectors. So I'm going to say that program is not repr C, but when I'm running the kernel function, which is here, will move from this to ops and constants. So ops will be a slice of op, and constants will be a slice of const. And the slice of const will be a slice of t, actually. And on top of that, we have, so the problem here is when the assembly, I mean, we can use a slice here, but we need to have a way for the kernel to know the actual size. So here I'm moving from activation kernel. So this is the implementation of that, and so here it doesn't match. So let's fix it. We have ops should be op. We have consts. So the thing is, I don't need to know. Well, we'll keep it simple, I guess. So we'll pass ops as ptr, consts as ptr. The problem with this is, so there is a value in not having more than 4 parameters, because they will land on nearly all architecture on the four register in the calling function. If we start putting more, we may in some architecture move to the stack, which is more difficult to manage. So I don't want that because I'm lazy. But I need one more argument. I need to know that ops is that we are done with the program. So either I'm adding there the slice of ops, but then I'm moving to, and I get 5 functions, 5 arguments. But I'm going to do differently. I'm going to add a done here. So every program will have to finish by done. And that, I still have a mosquito flying around. And that should allow me to know that I'm done, because I can check that the next op, if the next op is done, so 0, then well, I'm done. Which is, I think, how I'm doing in the other case. Yep, exactly. So we also have, we will reuse this system of comments because it was working pretty well. Okay. So next step. Next step is, I think, moving the implementation that we did last time in generic here and making it work. frame generic. So it's not frame. So in generic.rs, I will add activations. And so let's fetch last week implementation. So we'll start with this. Yep. And so I want this to be a function that match the CFFI protocol. So the CFFI protocol that we just defined in there, as in this. So we will be ops will be const op. I need to use op. Constants, there is a typo over there. So this will be a pointer to F32. Then we have buff. What is buff? That's X. And we have len as usize. And so this is a mut F32. Okay. So first things first, now A will be, so this will be unsafe. Most of it will be unsafe. So from row ptr, from row parts, std slice, from row parts. So I'm making it a slice again. I'm using XS and len. Okay. So doing the same. I cannot do it for the program because I don't know its len, but it's fine. And for the constant, I cannot do it either for the same reason. But it's okay. So the 0 and 1 stuff, that may not have been a super good idea actually, because no, it's not a good idea. We will redo it at the top level. I mean at the higher level if we want to, but we will not. We will stop this assumption. So now how to do this? So I'm going to loop, and I'm going to just op. I will call it PC. Make it mute, and it will be ops. And if and I'm going to do a match PC. Done not covered. Yes, thank you. break. Okay. Why is it complaining about this? Because there was no way to end the loop, but now there is one. Oh, match arm without brace. Okay, so it's something different. I don't want this. I want this. Okay, it's much better. I'm breathing again. Yeah, we'll see that later. So, we again have an issue with the types of these things. B used to be. So I want A, B, and C to be of the same type. So here, B is now a slice, which has to be mute, by the way. Okay, and my problem here is B. I need to make it a slice too. And for some reason, C is working out of the box. This is a bit weird. Okay, so now it's a matter of type F32 cannot be dereferenced. Okay. We have one less indirection that we used to have. I hope we can make it work again. Mosquito. Okay, U8 cannot be dereferenced. Const must be cast to usize. Constants cannot find value constants. Yes, easy one. So I need to change this a bit. It will be constant.add const as usize, and I will need a so add on a pointer just just the offset for each. Okay. Problem is I cannot make constant a slice again because I don't know its len. I would have to compute the max. So it's I don't want to do it. So I'm just going to do pointer arithmetics. Okay. Constant.add const as usize with a star. Okay. More of the same really. Oops. What did I do? No, it was okay. Yeah, I'm not sure what I did. Constant dot add const as usize. Yeah, it work. As usize. Okay, and more of the same. couple more. Okay. Finally, I need to put data back where it belongs. No, I don't need to, because now I'm just recapturing X, so I don't need to do that anymore. Previously, we were doing a copy, and so we need to put it back there, but not anymore. Okay, this seems to compile, so compute slice is not a good name for this function, because we want it to look like we want this function to look like something like it looks like the identifier of this implementation. If I look at how it's done in like, let's say here, for instance, so these are the implementations of okay, well, I'm just using generic. Okay, well, that's fine. I guess it's okay. I don't care. So let's now define our kernel. This as a kernel. So I'm going to call it S activations. And I will go ahead and paste all of these actually. So S activation, so the 4 at the end was for, in the case of the sigmoid, it meant how many elements we were going to loop over in the inner loop. But in this case, we did something different. We are operating on the entire vector at the time. We are doing allocation, but it's fine. I mean, this code doesn't have to be super optimized. Maybe this is not great because this code is also the code that we run on platform where we don't have optimized version. So I'm gonna just make it a to-do, make the inner loop title. So the idea would be to work over like 8 elements at a time or 64 elements at a time, something like that, instead of working the entire buffer. But for now it will do. So this will implement activation care. And I just need to fix the run function. Just need to fix the run function. Here we go. Oops. So we're checking that the X have the right alignment and the right len. I mean, the len must be a multiple of nr and the alignment must be respected. But instead of doing this, I'm calling compute slice with ops as pointer, const as pointer, and x as pointer. I'm doing it wrong. I shouldn't use this function. I mean, I should use a macro, and the macro is activation act ampl. Yes, yeah, we will do it the right way. So act ampl expect the type f32. The function will be generic f32 yeah, that will do nr. I don't have that many constraints actually with this code, so nr will be 1 and alignment items will be 1. Expected 2 arguments found 4. I'm not sure why the problem is. Okay, the problem is in macro. Yeah, no big surprise first time we use it. Here we go. So I'm calling, yeah, I need to here, yeah, this 2 needs to be consistent. So oh yes, and I think that's why I cannot call, this is why I must not use the macro, because the macro will assume that we have a function with a suffix. So let me check how I did for generic, if I did it by hand for the generic matmul. So the implementation now, here it's a bit long. Okay, yeah, I did it by hand. That's the implementation of the care structure. All right, okay. Nope, I cannot use the macro yet. The macro can be used with the actual external kernels, but not that easily with the inner kernel. So I'm going to hopefully undo. Yes. Okay. And so I was fixing, no, I was not fixing the macro. So xs.as pointer and xs.len as pointer mutable. No method as muteptr. Yes. Oops. I think I don't need to do this actually. Expected row pointer const found reference. So the question is, why is it working for this guy and not that one? src frame activations. Program and slice. What the what? I'm lost. I'm completely lost. Okay. So one thing at a time. Run takes up. Yes. Okay. This was wrong. Okay. And so here I will take program.ops and program.constants. Nope, not yet. Expected T found F32. So that's program need to be of T, where T is a lay datum. Everywhere. Okay. Is it compiling? Not yet. LA datum is not implemented for T. That's in this one. Yes. I think that should be enough, actually. Yes. Okay. So that's a different story now. That's a different problem. In generic, we have a parenthesis mismatch somewhere. Yeah, the unsafe bit. Okay. I forgot something important. So I'm not moving PC. So at the end of the loop, I should do PC plus PC goal PC.add1. Okay. So with this we have a reference implementation, hopefully, but we haven't tested it yet. So if we want to test it, now we need to look into, I mean, we already did tests, so we just need to port them somehow and fix them, because I changed the way the constants work. So I think I'm gonna copy all of this and fix it. Yep. I think I'm gonna need a subdirectory. Yes. Whoa. Okay. And so We have definition here, it will stay there, it's fine. And I'm going to add I already have a mode test here. I never remember if there is an S or not. So we'll see that later. Definitions. Copy all of this for now, at least. There. Yes. I'm gonna make it smarter. So TLA datum. Okay. And so now I'm putting back the constants where they should be. So this is going to be T0. Program of T. Taking T and T. And I can use 0 and 1. I'm not sure what this number are. Thing that VIM is showing. LA datum. Okay. So at least this makes sense for these. It's less obvious for sigmoid because for sigmoid we want to specialize the computation depending on the precision that we need. We don't need that many. We don't need that many coefficient with half precision and same for exponential, but we will leave this two alone for now and focus on the simple ones. Okay. Then the constant, so 0, 1, mulconst 0, also mulconst 0 because that's alpha. Alpha must be a T. Alpha must be T. Subconst 0. So yes, here we have a 0. This is an actual 0, so that's 1, and I'm going to put T0 here. Soft sine needs 1, so I hope that T is 1, yes. So here I need to add let's see, T0, T1, then this this guy, can I do 1 T1? Huh. Is there a smarter way to do this? One, two, three, four, five, six. Maybe there is a better way. But that will work. I don't know if maybe I have something like actually 6. Got it. Damn. Not much of it to know if it's which variant it is, but I'm pretty sure it's mosquito. Fuck. April. Okay. So what I wanted to do was 6 or T from 6. Maybe I have this. No, but okay, that will work. It's ugly, but it does work. I mean, or not. What's wrong now? Cannot divide T by T. Oh, T doesn't know how to divide itself. Ah, it will learn. src lib la datum. So what do we have actually? We have very little. We have add some mul. We don't have reverse. Okay. So I'm gonna add div, which should fix that. And I think given what I'm using it for, I should probably add this so if I'm doing T1, this is fine, over T from whatever 6. Ah yeah, from primitive, not the one I want. So this comes from num traits. Num traits, and from primitive always returns an option. And what I would like is something that cannot fail. So we are in the cast as primitive. Okay. So I'm not sure if I can say that. No, I cannot say that the implementer of ALA datum have to be a target of as primitive from F32. Okay. Okay, too much of, too complicated. I'm gonna stick with this. Oops. Where's my mouse? Where's my focus? Okay. All right, so now I have a couple of functions and I still need to implement the tests. So I'm going to move the definition that we have, the reference that we have in activation src reference. I'm going to move this code in src frame activation. Not what I wanted. Okay, src frame activation .rs. So this is I'm adding the references. Okay, and I'm adding some tests, which is a problem because I already have a mode called test. What's wrong here? Yeah. Frame activation tests.rs. And so we've already written some tests last week and the week before. src lib, and we can more or less use them as they are. So let's grab this. Close enough, I don't need it because now I have it, I guess. Scalar, I don't want it. Vector, that's the one I'm after. So let's take this. I'm gonna take this, so and what I want to do is I want to make it simple to call these. So for each implementation of the engine, cannot find prop test macro, try harder. Prop test. Really? It should be there. Ah yes, I know. Because I forgot to tag this module as a test module. Yes, so it tries to compile it without a test, and prop test is only included in tests. Okay. Nope. Let me just I'm gonna try starting it again. Okay, so now I don't want to write this. I want to write this once and for all. So still a bit of a problem here because we still have F32 explicit, but let's have a look at how it works for element-wise or for the matrix multiplier. So we have these frame tests. So I'm going to call this act frame tests. And so it takes a bunch of stuff. So a condition which is useful because sometimes we don't want to run a test on an architecture. For instance, when we are compiling Intel and we may be compiling on a computer without AVX 512, so we cannot run the test that are compiled with AVX 512. So in that case, the condition is a way to say should we run the test or not. So ker is the kernel. TATBTC we will keep TI, which is a type. And we are going to put all of these into there, I guess. And so I'm replacing F32 by STI. That should be fine. And so the only thing that I need is to make use of cond, and that's gonna be simple. Just do it the same way. And finally, compute slice. Yeah, compute slice. So I need to fix that one. I need to fix a lot of things actually. So what's the point here? I want to be able to write act frame test with, let's say, true for now, ker, so that's going to be our kernel, which I labeled src, and yeah, and I want this to live in just with the kernel, so that's going to be in activations. So here I have the kernel bringing up in Rust, and I just want this to live here with activations. And the type will be F32. Okay. So on frame activations.rs, we need macro, where are you? Mod test, macro export. And I don't like, I was never comfortable with Rust's rules for macro visibility, to be honest. Let's see if this is working. Mod test is private. I'm making it public, at least for now. And yeah, this is only in test situation, but actually I will move that. I will move this. So I don't want the macro to be defined all the time, but how did I do for... yeah, I'm having a look at how I did for this huge thing, but it might not be the best ideas, because it's overly complicated, and it's not necessarily super consistent either. So it looks like we have a macro use and config test. Okay, but we also have some tests that live in mmm/kernel, if I remember correctly. Yes, and they are tag macro export. Okay. So if I stop doing this, and if I just tag this as macro export. Nope, not yet. So do I need macro export on the intermediate? Oh, macro use. Yes, macro use. That's the one I want. So here I need a macro use this time. Whoop, it's better. It did something. Okay, so now what's wrong? So yeah, so this, I need to do something for that. Do I? Because this worked before. So what changed? Attempt to repeat an expression containing no syntax variables, because I'm defining a new function, and I'm not sure I understand what's wrong here, because what I wanted to do was define. Let me try to move this out of the outer macro definition. Up and see if it does something different. Okay, so let me make sure that we're not actually calling this in a non-text context first. So I'm going to put config test there. Okay. Yeah, so now it shows on TI. So putting back this and cond, of course. That was too simple. Okay, something is most definitely off here, but I can probably manage to define let's do this cond exp ti. Ti is a type. So now I'm moving the problem here. So I'm adding cond and ti to all of these. I can put ti back. And my problem is that prop test actually is not prop test. I need to import. So this is in prop test. Prelude. Yes. Okay, we're getting somewhere, because I don't mind if prop activation is defined once or for every. I mean, it's better like that actually. Let's try to enable the condition now. Something like that and like this. Okay. So we need to change this. So now it lives in definitions are in frame, activations, definitions, private. Okay. So I'm comparing I'm actually working on just the first item here. This is not the right test. This is a scalar test. And I need a vector test. Yeah. Okay. Well, it's okay. I'm still trying to make it work, and then I will fix it. So compute slice. So this so I'm given a program. Prop activation. I'm given a program, or I can obtain a program. Yeah. So here I have a program. That's my program. Let prog. Okay. And so I need to find. Yes, there was something missing. I knew there was a problem. So we also need the kernel here, or else what's the point? And so now we can do. So kernel, I said it was a type, but is it really? Because yes, it's a type. It's a type, and I'm going to. No, it's an instance, so it's an expression. Let's see how we call it. SRC activations, because I don't know how to instantiate it in the test. So SRC frame activation. No, it's in generic because it's on the call site of the test activations. S activation. So here I'm putting, well, it's both a type and an expression, so it's fine. Okay, so my kernel is an expression, and I will call so I'm a bit lost because what I'm doing here is a kernel level test, and I'm not sure that's what I want. I mean, it will make sense to make kernel level test for sure, but it doesn't. It will not test the frame iteration mechanism. Is the problem? I don't think so, actually. I mean, I will test the rest separately, and it's just source code, so it doesn't need to be tested on all implementation. Because the question is, should I pass activations, or should I pass, which is a kernel, or should I pass a frame, the frame level activation object, the one that knows how to realign data and stuff? No, I will just pass this one for now. So kernel is a kernel, and so on the kernel I can call run with src activation just to see src frame activations. So I'm going to call that one. So I'm given a program, so I can do ops is prog dot ops prog dot consts constants, and my vector is slice. Okay, progress. Why? Because I forgot. So it's a type. It's a type after all. It doesn't have a self. Okay. Okay. So it will be called like this. And I think there is a trick in macros. Yeah, okay. Prog ops is private. src frame activation .rs and program. This has to be made pub. Okay, and it's consts. Okay, so it's better, but it's not perfect because here we are just testing for 1x the slice, and I want to test with at least nr values, because I can only call the kernel with with a multiple of nr. So I will need to change the rules. I will need to change the rules here, and we will say actually what I'm going to do is I'm going to because our test is I mean no, this is wrong. Prop activation, putting a prop test like this, and oh yeah, that's correct. I can add stuff here. I'm allowed to, because so I need to call the kernel with 0, 1, 2, 3 times nr data. That's the contract, and it has to be aligned. So the question is, I think the right way is to repeat x over, I mean, to compute uniform chunk of data, and to repeat it over a couple of frames. So I want to do in 1, 4. This should work, and so I'm gonna do slice equals. So I want it to be aligned. So that's always a bit of a mess to do. So I want to allocate a buffer, an aligned buffer. Maybe I already have stuff to do that in tests. Well, of course I have. Of course I can do that. Let not input equals tensor 0 aligned. So I'm going to make it k nr times repeat single dimension slice, and for the alignment I'm going to use k alignment bytes. Here we go. Let's see what it says. Cargo check. Cargo watch. So there are problems of wrong unmatched parentheses. So that's the cond as a function, that's a prop test. This is okay, it's better. It's actually nearly compiling. expected expression. Okay, so k is not k, it's care in this context because I'm in macro. And in the macro, we need this magic syntax to call stuff on a type. So I have my input. Then, okay, tensor, it doesn't know. Come on. Tensor is in tract data. Okay, zero aligned. Starting to be tired actually. Docs.rs tract data. Tensor. And I have zero aligned. Zero aligned. Okay, and it seems fine. So the slice, it will be, so I need to write x as slice mut of ti dot unwrap dot for each. So I need to copy x all over the place. T equals x. Okay, and here I can use input.asSlice mut of ti. Okay, dot unwrap. Okay, we're getting somewhere. These two are not working because I haven't decided what to do with them yet. So I need to run my reference data on, and yeah, and now I need to check that for let expected equals, so create frame activation reference name of x, and I need to do a slice for y in input as slice, yes, unwrap prop. Is it the right way to do this? Expected, should I compare each element, or should I compare the entire tensor? But if I want to compare the entire tensor, I need to make, yeah, well, it's the same actually, so I can do that. Let mut output. I think I have a creator for, instead of 0, like a fill t with value t, yeah, and that's it's a mutator. Okay, but it simplified this, So it's input.fill by x. Okay, and so I can do the same for output. So output will be, it wouldn't have to be aligned actually, but it doesn't hurt. So that's the same, and output dot fill by expected. I need to add the params here. S params. Frame activations dot rs, and I need to make reference public at least for a while. Okay, what's next? Repeat. I need to make it use size. Okay. Do I have my test? I forgot the comparison. So that's output.fields. This is redundant now. And I need to do output.close enough input to unwrap. So output is a tensor. Yes. Okay, segfault, excellent. So let's try to make this work, and then, I mean, for a couple of minutes, and then I'm stopping right there. SRC generic activations. So first thing I'm gonna check is I don't even know what it's trying to run. So first I'm going to do no capture and test threads equals 1. Okay, oh, so 2 of them have been working. Hard switch is the one with the super weird. Oh yes, I forgot the down thing. So SRC generic SRC frame / activation reference, no definition. So I decided not to put the length of a program, so I need to say that when we are done. Done. And that's it. Okay, we're not there yet. We are reading some weird stuff. So it's already failing with relu, which is a good news because that's an easy one. So let's do debug PC. And generic activation relu. It's still a prop test, so it's still doing a lot, which may not, which may be a problem for us. I don't know why it's running this one. Ah yes, because I have two selectors. Okay, so relu is failing with a big error. PC here seems wrong. So we have max const of 0. That's correct. And then we are crashing. So PC add 1. Then we should jump there, and we are basically exploding on that. Let's check. Yes, relu is I missed it. Hey, that's better. This is much better. So let's try it like that. Okay. So what is happening here? Let's check our definition. Hard. So 2310, 2310. We have 4 of them, so it should be fine. We haven't forgotten the node down. So let's look at whatever we're reading. So we have a super big value. We have a super big value. And okay, so super big value. What are we doing? And I don't know. Yes, A, B, and C must be small, so we can print them. A, B, and C. Or A and B actually, it's enough for this one. Pom pom pom. Okay, so PC is move BA. A is full of these super big values. B is 0, so then it didn't work. So these values should have been copied to B and they were not. So I've broken the move function somehow. Blah, 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 blah. yeah, I think because I removed some stars and maybe that wasn't the right thing to do. So here we have debug. I'm going to use this because it's more compact. Regs and debug. Okay, so I'll move. Where is the move? Move is here, so before and after B isn't changed, so something rare is happening. We are moving A to B, so destination, so we are in the second case. Let's see what's okay. So D is all zeros, which is expected, but S is all zeros, which is not expected. We Oh, I think I know what's wrong. DST and SRC. Yes, this is it. I think. Yes, all green. You can remove the debug. Still, there is still some. SRC generic activation 26 debug. Okay, it's not too bad. Let's see what's happening there. It seems all green. Yep. So with this, we are about ready to start writing assembly. I hope that it will be today, but no. It's not. We're not there yet. I think we'll be next week. But at least we've moved everything in tract, and it will make it much easier to write the assembly next time. because we have many examples that we can cut and paste from. So that's it for today. Oh, wow, there was a question in the chat. So there was a viewer. I don't know where it was. Are you using my own assembler? Yes, I'm defining my own assembler. I'm writing it, I'm implementing it, and I will implement it on the regular assembler at a later stage. Not sure if there is anybody listening. I will check rapidly. But I think nobody's watching. It's like in space. I can shout. Nobody is going to hear me shout. Pum pum pum. Oh, pum pum. You're still there. Good. Oh, pum pum. You're still there. Good. Oh, yeah. So, well, yeah. In a few words, yeah, so I'm defining in kind of VM. In a few words, yeah, and that's kind of VM. In a few words, and that's defining these programs and it's simple using these programs element-wise functions simple visualizing programs and hopefully next time we'll try to hopefully next time we'll try to hopefully next time we'll try to hopefully next time and yeah, that's it for today. Thanks for watching. That's it for today. There was one viewer. That's it for today. Thank you, and there was one viewer. See you soon. That's it for today. Thank you, and there was one viewer. See you soon. That's it for today. Thank you, and